Well, in this video lecture, we are going to apply the Kuhn-Tucker condition with a practical example. In the previous video lecture, we discussed the condition and the logic behind the Kuhn-Tucker conditions. But in this video lecture, we are going to take an example from mathematical economics, right? We are having a profit function, and we want to maximize this profit function subject to this given level of output. And note that this is a single inequality constraint, right? We will optimize another economic function subject to multiple inequality constraint in the upcoming video. Okay, so let's see how can we apply the Kuhn-Tucker conditions to maximize this profit function. All right. So first of all, we would like to set the Lagrangian function. So report the profit function plus lambda time rearrange this inequality constraint. Note that in simple Lagrangian multiplier method, in which we use the equality constraint, there is no restriction over whether you shift the left hand side to the right hand side or you shift the right hand side to the left hand side. But in case of Kuhn-Tucker condition, you have to shift the left hand side to the right hand side carefully. All right. So this is Lagrangian function, right? So first of all, we would apply the we would report the Kuhn-Tucker condition as follows. The first half conditions are these three, and the second half condition are the rest of the three conditions, right? These three conditions they maximize the Lagrangian function subject to the independent variable x and y, right? And the rest of the three conditions minimize these three conditions. They minimize the Lagrangian function with respect to lambda. That's why the Kuhn-Tucker conditions seeks out the saddle points, which on one hand maximize the Lagrangian function subject to the xi, and on the other hand it seeks out the saddle point, again the same saddle point, that minimizes the Lagrangian function with respect to lambda, right? So what are these first three conditions? You take the derivative of this Lagrangian function with respect to x, and it should at most be equal to 0. Then again, the derivative of this profit function with respect to y, and it should also be at most equal to 0. Then second condition is the saddle point should at least be equal to 0. Similarly, the saddle point y bar should also be at least equal to 0. And then the complementary slackness condition. So these are the first three conditions. The second three conditions are, you take the derivative of the Lagrangian function with respect to lambda, and it should at least be equal to 0. Note that in the first half, the first condition is, 1a condition is, it is at most equal to 0. It is because we maximize Lagrangian function over here. But since we know that we minimize the Lagrangian function with respect to lambda, that's why the first order derivative of the Lagrangian function with respect to lambda should be such that it should at least be equal to 0. It means that it should be greater than or equal to 0. The second conditions are the same, right? In the same way, the third conditions are also the same. What is different between the 1a and 2a is, we put it at most equal to 0 and we put it at least equal to 0. Now we have to check these conditions. You have to report it. Now you have to check these conditions one by one. How can we check it? Look at it. We are starting from 2b, this condition. You should start from over 2b, from over here, right? Since it is at least equal to 0, it means that lambda bar is greater than 0 and our lambda bar is equal to 0. So we are testing it, right? So where would we test it? We would test it in 1a. the first condition in which we, that is, the derivative of the Lagrangian function with respect to x and the derivative of the Lagrangian function with respect to y, right? So if you put lambda is equal to 0, starting from testing lambda is equal to 0. If you put it equal to 0, it would be something like this, and you will get the value of x bar, it is at least equal to 16. Similarly, if you put lambda equal to 0, lambda bar is equal to 0 over here. So again, you should put it lambda bar equal to 0, right? And you will get the value of y bar, which is equal to y bar is at least equal to 0. So we got two critical values, that is x bar and y bar, right? Now we would test it whether it satisfies the given constraint or not. So we have to put the value of x bar and y bar in the constraint. So if we put x bar is equal to 16 and y bar is equal to 12, it is equal to 28. 28 is not less than or equal to 20, right? According to constraint, x plus y should be less than or equal to 20, but we got 28. So these critical values does not satisfy the given constraint. So what we conclude that lambda is not equal to 0. We got this point. If lambda is not equal to 0, then lambda is definitely greater than 0. So one situation is cleared, which is lambda is greater than 0. So 2b is clarified, lambda is greater than 0. So what we do is, you have the condition 1 verification is, you have to test whether lambda is greater than 0 or it is equal to 0. It is confirmed. Turn to the second condition. The second condition is, we know that this is 2c, right? It is already clear that 2c is lambda bar, either lambda bar or this constraint is equal to 0. But since this is confirmed that it is greater than 0, so definitely it is equal to 0. So this is also been confirmed. 2c is also confirmed. And we conclude that the constraint is equal to 0. So this is the second condition. This is linked with the first condition. We clarified this, right? Now comparative with the 2c. 2c is either lambda bar or this constraint is equal to 0. Since this is greater than 0, so it means that this is equal to 0. Turn to condition 3. Condition 3 is, you have to test whether the solution would be boundary solution or it will be an interior solution. So we are testing for boundary solution. Okay. If x bar is equal to 0 or y bar is equal to 0, then it would be boundary condition. However, if x bar and y bar are greater than 0, then the solution would be interior solution. So how would we check this? We can check this by testing, putting x bar equal to 0 in the 1c condition, in which we which is either x bar or this constraint would be equal to 0. Similarly, y bar or this constraint would be equal to 0. So if one thing is clarified, the other thing would be automatically clarified. For example, if it is clarified that x bar is greater than 0, then it would be definitely equal to 0. Similarly, if it is confirmed that y bar is greater than 0, then this constraint would automatically be equal to 0. So let us confirm this. Suppose we assume that x bar is equal to 0. If x bar is equal to 0, put it in the constraint, right? Because this is 20 minus x bar minus y bar is equal to 0. It is already confirmed from the previous condition, right? Since lambda was not equal to 0, that's why the constraint was found equal to 0. So if you put x bar is equal to 0, y bar is equal to 20, right? put y bar is equal to 20 in this equation, right? So if you put it in this equation, it would be something like this: 20 into 96 minus 8 times 20 and minus lambda bar, but lambda bar is positive. So if you look at it, it is not equal to 0, right? So that's why we conclude that x bar is not equal to 0. This is not confirmed. Similarly, if you test y bar is equal to 0, if you put y bar is equal to 0 in the constraint, the value of x bar is equal to 20. So if you put in this equation, right? So putting x bar is equal to 20 in this equation, 20 into 64 minus 4 into 20 minus lambda bar, but lambda bar is already greater than 0. So if you look at this calculations, overall its value is not equal to 0, so that's why this is not equal to 0. So what we conclude that neither x bar nor y bar equal to 0. So when neither of them are equal to 0, the solution is an interior solution. It is not boundary solution. Okay. So what we conclude is we have seen that neither lambda bar nor x bar and nor y bar equal to 0. So neither of them are equal to 0. So we turn to equation 4, condition 4, sorry. Comparing 1c and 2c, look at it. 1c contains these two equations, right? And 2c contains one equation. And we have seen that neither of these variables is equal to 0. So what we conclude that these three equations are equal to 0 without x bar, without y bar, and without lambda bar. So putting them equal to 0. So we have put these equations equal to 0, and we are making a system of equations, system of linear equations from these three equations, which contains x bar, y bar, lambda. You can see there is no y bar over here, so we put 0 y bar over here. There is no x bar over here, so we put 0 x bar over here. And you can see there is no lambda bar over in this over here, so we put 0 lambda bar. Decomposing these equations into matrices so as to solve it for lambda bar, x bar, and y bar. So we got these three equations, right? If we take this equation and we name it as equation A, and we find its determinant is equal to 12. So what this 12 is? This 12 is actually a determinant. This is a determinant. Okay. Now we are making three matrices of it, right? We are making three matrices of matrix A. That is, we are constructing matrix A1, A2, and A3 so as to apply Cramer's rules to obtain the value of lambda bar, x bar, and y bar. Okay. So for A1, we would ignore the first column and it will be replaced by the right hand side. It will be replaced by this matrix. Look at it. Then we will ignore the second and it will be replaced by this column. Then we will ignore the third column and it will be replaced by this column, All right. So look at it. For A1, the first column is replaced by this matrix. For A2, the second matrix is replaced by this column, right? And for A3, the third column is replaced by these columns. So we got three matrices, A1, A2, and A3, right? So this is the determinant of A1, this is the determinant of A2, and this is the determinant of A3. So if find the determinant of it, we will get these three values. And according to the Cramer's rule, if you want to obtain x bar, it is equal to A1 determinant divided by A determinant, and its value is equal to this. If you want to obtain y bar, it is equal to A2 determinant divided by A determinant, its value is 9.33. If you are interested in lambda bar, it is equal to a 3 determinant divided by a determinant is equal to 21.33. So how can we interpret the value of lambda? The value of lambda is equal to 21.33. Okay, it means that if you are increasing the constant and the constraint, which is the given level of output, which is 20, right? If you are increasing the constant in the constant, which is 20 in our case, by 1 unit, it means that if you are increasing it to 21, your profit will increase by $21.33. So these are the saddle points, right? And this is how to apply Kuhn-Tucker condition, which are necessary as well as sufficient condition for the optimization, in our case for maximization. And this is how to apply it for the maximization of profit function subject to a single inequality constraint. Thank you guys. The only thing that gives me more energy, more happiness, more motivation to create more videos for you guys is your kind response. Thank you. Thanks for watching. Stay happy.